everyone, so today we're going to solve exercise 6.6, which asks us to prove that for all natural numbers n and for all positive integers m, the expression m to the n minus 1 is divisible by m minus 1. And so let's first make sure we really understand what this means. What we're essentially saying here is that if I pick any positive integer m, like 5 or 10 or 100, and we raise it to any natural number power n, and then when I subtract 1, the result will always be divisible by m minus 1. So the hint here is to fix m as arbitrary and perform induction on n, and this is a great strategy because we're trying to prove something for all n, which is exactly the type of scenario in which we would like to use induction. So let's try and set this up more formally. First, knowing that we have to do a proof by induction, let me make this font size a little bit bigger. As the hint states, we want to let m be arbitrary and fixed. In this case, we're going to perform induction on n. So let's let p of n be the statement m to the n minus 1 is divisible by m minus 1. And we are going to prove that this holds for all natural numbers n. Okay, so the first step with any sort of induction problem is obviously establishing that our base case holds. In this case, since we're dealing with the range of natural numbers, our first possible natural number is 0. So in this case, our base case is that n is 0, and so more concretely, we need to show that m to the 0 minus 1 is divisible by m minus 1. And now we know m to the 0 minus 1, anything to the 0th power is just 1, right? So this side becomes 1 minus 1, which becomes 0. And, since anything is 0 is divisible by any number, any non-zero integer, we know that our base case holds. Alright, so now that we've established our base case, we need to establish our inductive step. And this starts with our inductive hypothesis. In this case, we only require weak induction because we only have one base case. We don't need to prove this true for any sort of range of numbers. So our inductive hypothesis is to assume p of n holds for some arbitrary n in the range of natural numbers, and our more concrete goal is to prove p of n plus 1, which in terms of this specific problem means we want to show that m to the n plus 1 minus 1, erase this here, is divisible by m minus 1. So let's consider m to the n plus 1 minus 1. By just our knowledge of exponents, we know that we can rewrite this as m times m to the n minus 1, like so. And now we can think about how we want to manipulate this further to sort of get to this this goal here. And so what we can do is we can use a clever trick and add and subtract the same term, m to the n. So what this can be rewritten as is m to the m minus 1 plus m minus 1. Yeah, so now that we've reached this point in rewriting, we know that obviously by the inductive hypothesis, m to the n minus 1 is a multiple of m minus 1. So we can write like so. And thus, m times m to the n minus 1 is also a multiple of m minus 1. And obviously this term here is a multiple of m minus 1 because it is m minus 1. And therefore this entire sum is a multiple of m minus 1. And so this completes our induction. So let's write this a little bit more formally, since we just did, a bunch of math to try and figure this out. We can write that by the inductive hypothesis, there exists some integer k such that m to the n minus 1 equals k to the m minus 1. So we can then write m to the n plus 1 minus 1 equals m to the n, m minus 1 plus k times m minus 1, which equals m to the n plus k times m minus 1. And so this shows that m to the n plus 1 minus 1, this term here, is equal to m minus 1 times the integer m to the n plus k, which means thus that m minus 1 divides m to the n plus 1 minus 1. And therefore, p of n plus 1 holds, and this completes our inductive step. Therefore, by the principle of mathematical induction, p of n holds for all natural numbers n. We can write that concretely. By principle of mathematical induction, p of n holds for all n in the set of natural numbers. And since m was arbitrary, this holds for all m in the set of positive natural numbers as well. Yeah, and that's our proof. The key insight here was this sort of clever algebraic manipulation part here, adding and subtracting m to the n, lets us split the expression into two parts that we can handle with our inductive hypothesis. So, thank you.